Sorry. Okay, Bismillahirrahmanirrahim. So welcome to the online class today of theory of computing. Today actually I will try to cover very few content, and we will do some practice. So I request my dear students to keep with your notes so that you can participate in the practice sessions. Okay, we'll try to practice at least 5 example for finite state machine, and we will learn. So first things we are going to complete today we already covered the definition of finite state machine. So I will review, and then will see some example of finite state machine. Then there will be one slide. What is the meaning of computation? So we'll define today the computation. After that, we'll start discussing regular language. Last class, I already talked about a bit regular language, so we'll cover that definition. And once we cover this definition, there is some operation we can compute on the regular language. So that operation is called regular operation. So we will see, and maybe subsequently next week we'll prove that operations, inshallah. And during this class, I will take your attendance maybe any time. So remain alert, okay? So let's start. So last class, as we are talking about that finite state machine or FSM, it's also called finite automata, okay? It's also called the finite automata. Is a simple mathematical model, or computational, we can say computation model for computing to recognize some pattern within input string. And you know, this string we actually means that the problem statements or instance of a problem encoded as a string, okay? And we know that in the finite automata or finite state machine consists a number of states, finite state and transitions. And we give the finite state machine or finite automata, both are same. It has 5 items or 5 tuples, right? So these are the first one is the state Q, set of state. There could be more than one states, and sigma denotes the symbols, set of symbols. Delta represents the transition function. That means how the machine moves from one state to another state. That is determined by the finite this transition function. Then we have initial states. You know, every machine should start somewhere. So we designated some state as the initial state, that where the machine actually start to working. And definitely at the end, once the computation is completed, then we definitely should end some state, and that state known as a final state. So the final state is the states where the computation end or completed. So we know that automaton is a singular of the finite state automata, is a simple models, reads the input string symbols from the alphabet and changes the states according to the transition function until the input ends, right? So we scan from the beginning of an input, and if we end at the end of the input and we reach to the final state, then we say that this string is actually accepted by the machines, right? So overall the workflow is we start some starting states, we read input symbol from the alphabets, and we follow the transition function to move from one state to another state. All right. So the formal definition we already discussed in the last class. We have these 5 tuples, and this where Q is the finite set called the states. The lambda is the finite state called the alphabet, and the transition function, you know, we are in some state, we read some input from the alphabet, and we move to the state. That is called transition function. And Q naught is a member of the state, and definitely is called is starting states. And last class we told that in a finite state machine there is only one starting states. And F is also subset of Q. You can now understand why it is subset. That because the final state could be one or more states, or maybe all the state could be final states. It's possible. Okay, that's why final state is a subset of Q. Okay, so please remember this, that Q naught is belongs to Q. It's only one member. It's not a subset. If you see these two definitions or two lines, okay, here, and but the final state is a subset. Why? Because more than one state can be a final state. And as I told you, maybe all the state could be also a final state, and one of them could be a starting state. Starting states could be also a final states, right? Last class we saw that examples. Today we may also have some example today. So suppose in the final state machine, we have states Q naught and Q1, and alphabets we have 0 and 1. That means input strings consisted of 0 and 1. Then what does it means? That lambda, you are in the state of Q naught, reading 0, you going to new state that is called Q1, which means on the input 0 we have a move from Q naught to Q1. Okay. Again I am repeating, what does it mean? This transition function, as you can see here, the delta Q naught reading input 0 and it's moving to Q1 means that on input 0 I am moving from Q naught to Q1. On the other hand, if you are in the Q naught states and you have current input 0, then you are moving to Q1 states. Okay, I believe this definition is clear and you are able to write without memorizing this definition, inshallah. Okay, so I will request you, my dear students, to try to understand what this machine or this final state machine M1 accept what kind of language. This is our task. We want to define the language that is being generated or accepted by that machines. So how many states are here? You can see there is 3 states, Q1, Q2, Q3. And Q1 is the starting states, Q2 is the final states. And what are the symbol or alphabets are here? Definitely, since the transition are labeled with 0 and 1, that indicates the symbol or alphabet for this machine is 0 and 1, 2. Now, if I try to simulate and get what language does this machine accept, can you try first what language this is accept?
Sir, the string should end with 1.
The string that ends with
1.
1. Exactly correct. Very easy, right? Thank you. So this is my states Q, Q1, Q2, Q3. And this is my alphabet 0 and 1. And lambda delta is my transition function. Q1 is my starting states. If my final state is Q2, and this language W contains at least 1, 1, and an even number of 0 followed by follows the last one. Even number of. Is it correct?
I think, sir, no. I mean, because
Ah,
we might have 1 0 and 1 1.
yes, right. Thank you. So it is not correct actually. It's the simple definition is W contains at least one one at the end, right? That's all. So I requesting you to correct this one. Okay. So this language actually accept the string that has at least one at the end. At the end, at least one. Okay. Okay. Now let's try this language. What language does this accept?
Zero and one.
Zero.
And one.
This is the correct one. This one the same. I think the previous one is almost the same, but it's different. It's I have drawn here with two states. W ends with one. Definitely, it ends with one. Okay. What about this? Sorry. Yeah.
Always ends with a zero.
Always ends with the zero. Excellent. And anything else? Is zero is the member of this language? Only zero.
Also an even number of ones.
Even number of ones. I'm not. It's not correct because one and this go to the zero. So only one. The answer is correct. That's it's end with zero. This machine ends with zero means if it is a machine of binary number, what does it means? If any binary number ends with zero, what does it means?
It's an even number, sir.
Even number. And also another way we can say it divisible by
Two.
2. Okay. So this strings, since the starting states here is the final state, so how I can go to the starting states? Do we consume any input, any string to go to starting states?
No.
No, right? So that means when I am coming to this starting states, it's also accept empty string. Epsilon. Do you remember the empty string or zero length string? So this machine also accept empty string. Okay. So W is a empty string or ends with zero. In other words, I can define say W is an empty string or divisible any binary number divisible by 2. Okay. Any questions so far? All right, let's try the next machine. Now the machine gets a bit complicated and it has 5 states: S, Q1, R1, Q2, R2. There is a 5 states and how many symbols are there? What are the symbol or alphabet of this machine?
A
A
and
and
B.
B.
Very good. Thank you very much. So now try to dissect what is the language for this machine.
ends with either A or B.
A, either A or B. Is A bit correct? But still, I'm looking. Try to simulate for few strings, both direction, A direction and B direction.
Sir, either starts with A and ends with A, or starts with B and ends with B.
Yeah, that means start with the same symbol and ends with the same symbol. Is it clear? So if some machine need require that start with the same symbol and ends with the same symbol, then we can say that is the correct answer. Okay. And also, if I say that write the strings from A, B that start with the same symbol and ends with the same symbol. In this case, only B also a valid string because it start with B and ends with B. Or if you say only A is also a valid string because it start with A and ends with A. All right. So thank you. You have successfully dissected the language that this machine accepts. So M accept string that start and end with the same symbol. Thank you. So far we've seen some examples. Maybe in the class we'll do practice more, and then tomorrow in the Thursday, hope you will be in the physical. We will have physical class. We'll try to. Today I'll give you one homework. It's a bit difficult, but I hope you can able to solve it. Okay, let's try to now discuss about what is the definition of computation. Actually, you know, right? When I have a string, like suppose for this machine, if I gave a string, please, I cannot able to write. Can I write? Let me try. Yes, I can write now. Suppose if I write A, B, okay, B, A. This is a valid string, right, for this machine, isn't it? Start with A, ends with D, and there is a multiple B, right? So start with A, come with this B, and loop with this B. So A, B, B, and then come to back to this final state with A. What is called what we did actually. Now, if I ask whether this string, suppose A, B, A, whether this is a valid string for this machine, if I ask to you, or maybe I ask that whether this string is generated by this machine or not, what you will do? You will be in the starting states and you look at this first symbol of this string, right? That you have now A, so you move to Q1. So let me try to simulate. Did you get my point? If I ask you that whether this string can be accepted by this machine or not, how you do the computation? What you will do, you will come to the starting states and you read the input, first input A of the string, and you move to Q1. Now it takes to Q1. You are now in Q1, and now you move to your next scan because now you have A, right? So since you have A, you remain on the same state Q1. So still you are in a Q1. Next you consume which in string input. Next you consume input B. And once you read B at Q1, you will move to Q2, right? So now you move to Q2. Once you move to Q2, your current input is A. So if your current input is A and you are in Q2, what you are doing, you are moving to Q1. So you move Q1 and your current input is A. Once you read this input A and you remain Q1, so at the end, you have no input. It means you read or scan all the inputs from the beginning to end, and you are now at Q1 state. And we know that if you scanned all the inputs and you are in the Q1 state, that means what? And Q1, if the Q1 is final state, that means this string belongs to this language, right?
Yes, sir.
So this is called actually computation. We did computation. Okay. So what we did again, let's try to understand the definition of computation with the example that when a string is given, I will start from the starting stage and try to scan the all the input. And if we are at the end of my string and we are in the final state, then we can say that this string is generated by this machine, or on the other way, excuse me, or in the other way, that this string can be generated by that machine. Excuse me. Okay. So that is called actually computation. So now let's go to the definition of computation. What is does it called? So we have a finite state machine. It has 5 states. Be finite automata. Let W is a string. So this in the example, this W is my string, okay? And it consists some alphabets, W1. So this is consists of some alphabet. This is the length of n. Be a string where each WI means this, or each of this W is from alphabet, right? So here in this language, our alphabet was AB, right? Our alphabet was AB, so the strings are built with AB. So that is the formal definition we try to understand. So I hope believe with the example it will be clear. Then M accepts W means this string will be accepted if there exists a sequence of states, right? Exists a sequence of states. You can see there exists a sequence of states. Here is R0, R1. Here it may be Q1, Q2. In Q, satisfying that the first state is initial states, and then correspondingly from each each state, you consume next symbol, and you went for the next state, some other state. And if the Rn, this is the final state, if this is belongs to the member of final state, then that is called computation. Is a complete computation. So you can see here we have sequence of states, and definitely we started S, right? Definitely we started S. We didn't even written here. We started S, and we follow sequence of state, and we end the string, and we are at the end of my final states. So this string accepts. So the machine M accepts the W or strings, and that is called actually we say that M recognize the language L means M accept W means you got the point. So all the strings are accepted. So what are the condition? The machine start at the starting states. It transit according to the delta, and if it accepts, if it is N, the accept states. Okay, so that is called the definition of computation. This is just a mathematical term. What is the meaning of computation? Here, computation actually means we are scanning at the start. We are scanning strings, and we follow all the string to the end, and we reach. If we reach in the final step, then we call that strings actually accepted by that machines. So that is also another term is called computation. What computation are actually happening? Okay, so it is written here in a mathematical format. Okay. All right, so let's move on. Is it clear? So now we are going to, I think we started this one. A language is called regular language if some finite automata recognizes it, right? I think I also covered this definition last class. So in other words, if there exists a finite automata, if there is a machine is there for that language A, suppose your language I define A, and that machine accept this A, then A is called regular language. So if a language is regular, that means we have a finite state machine for that language to recognize or to compute that language or to solve that language, whatever you can say. So if the two language are regular and if we perform some operation, that language actually called the that operation is called regular operation. Okay, so before going to the regular operation, now I will give you a simple task. Okay, please send your last 3-digit ID into as a message. Last 3 digit of your ID into the message. This is your attendance today. I am repeating. Those who joined, please send your last 3 digit of your ID. Thank you. If you miss to sending this digit, then you miss also the attendance. So please be careful. And no one can send other one, okay? Thank you. So one person can send only one. No proxy. Thank you. Okay, let's go. So regular operation. Suppose we have a two language, L1 and L2, and suppose this and we define a regular operation union and concatenation and star. So you will see another new operation is here. I need to write something, so I'm minimizing the slide. Union, you know, if I want to make union of two language, what does it mean? That I have a new set that any member of this language, this X, or means this is a string or problem statement either from L1 or either from L2. Okay. It's very simple. Then concatenation, if I have two language, L1 and L2, and X1 is a member for, X is a member for L1 language, and Y is a member for L2 language, then the concatenation actually XY. How it's coming XY? It's X come from L1 and Y comes from L2. I'll give the examples. But now there is another new operation. You may be not seen this operation that is called L star, and it's a very useful operation in the theory of computation. Okay, so L star actually define the combination of many strings where this k could be 0, means it can also have zero length string, means epsilon is also member of this language, and each xi from L. So this x are coming from actually L. So combination of any form of combination of x you can form actually A star. So let's look at an example, then that maybe become more clear for to you. So here note the star operation is unary operation because it's only performing on symbol or single variables or operands. So it's a unary operation. It works by attaching any number of string from L together to form a new string. Any number you can take and attach and place each other before, after, whatever. By combining as many possible there, you can just combine it, because any number means it also include zero length string also means the empty string is always in L star, no matter what L is. In L, whatever it has, it also epsilon is also a member of this string. Why? Because we said that any number also includes zero. That's why zero. Okay, let's see the example. Suppose I have two language L1. L1 has two string. One is good and another string is bad. And L2 is another language which has a boy and a girl. Then if I try to make L1 and means binary operation on L1 and union operation on L1 and N2, what we'll get? We'll get all these members union by this. So the new language, so maybe suppose this is a new language L, which is equal to L1 union L2 is consist all the strings of these two language. It's as easy as possible. So simple. Next, concatenation. So if I try to make L1 concatenate with L2, a new language L, then definitely first member comes from L1 and the followed by member will come from L2. So if I take good L1, then second part will come from the L2, boy or girl, whatever it can come. So it makes 2. And next, if I take the bad, then any of these two can add it or concatenate it with this bad. So bad boy, bad girl, it could be there. Okay. So these are the new language concatenation by the concatenating by these two language. Okay. This is a new language. Now, what about the star? So it's L1. Now I'm taking only L1 because I don't need 2. I need only 1. It's binary operation. So any form of good, bad, okay, you just attach any form before, after, whatever the numbers. So the first one, epsilon, because I am not taking any of them. And then you can take only good or only bad, good, 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 bad, bad, good, bad, bad, whatever is infinite, say, length of the sets can be possible. Okay, so this is called A star or L star operation, star operation. Is it clear? So you can take thousands time good, 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 and one time bad is also possible. So infinitely many combination are possible. A star. Okay. This operation is very useful for this course, so we try to understand this one. All right. So far, from today, our discussion will be divided into two parts. As you can see, I am writing DFA, that means deterministic finite automata or deterministic finite state machines. Deterministic means, what does it mean? It means that exactly one transaction per symbol. So far, whatever the examples we saw, with one symbol, we have only one transition, right? A, we have only one. We don't have with B, we am going here also. We don't have this kind of transition. You will never see. Only one transition from one state to one transition only consume one state. Same symbol cannot be consumed by the same state to go multiple places. Means there is no parallelism. Only one state you can move. Okay, that is the meaning. I'm repeating again. So exactly one transition for per input symbol. For every state, a deterministic finite must have one and only one transition defined by each input symbol. So means one input symbol can only have a one transition from one state to another state. And the next is uniquely determined by the current state and input symbol. So if I have A, that means current input A, so this will be determined where I'll move from the next state. Every state must have transition for every symbol. You can see this is the one of the crucial things that I am going to discuss. Again, very carefully read this. Every state must have a transition for every symbol. Okay, again, I am repeating, please, my dear students, pay this attention. Every state must have transition for every symbol. What does it mean? Let's go to see. Okay, let's look at this example. In this language, we have only two symbols, A and B. So see, S has two symbols, two transition with A and B. Similarly, Q has either A or B. Similarly, Q2 has either A or B. Similarly, R1 has either A or B. Similarly, R2 has either A or B. So each state has transition for each symbol, for every symbol. Okay, if you have that thing, that is called deterministic finite state machine. So no input symbol can be missing or left undefined for any states. So in summary, the DFA is deterministic because it never has multiple choice or never lacks a transition. Means from each state, you consume all the symbols and you move forward to next state. Okay, so now let's look at this next example, then it will be makes your idea what I'm talking to. So this is an example. First of all, what language this machine accepts? It's very simple. If you are in the state A, if you have first input 1 and next 0, then it will expect you are end with this E state. That means this language accept only 1, 0. Or if you start with 0 and end with 1, many number of zeros and end it with 1. So this is the possible. So this language actually accepts W is either 1, 0 or a string of at least 1, 0 followed by a single 1. If I ask, what about the triple one? Is this string belongs to this language? No, thank you. What about the 1010? No, so this is also not possible, right? So these two strings are not belongs to. Okay, in the previous slide, I just discussed these things that every state must have a transition for every symbol. What are the symbols for this language? For this machine, what are the symbols? Okay, 0 and 1. And I also said that for every state, DFA must have one and only one transition. And sorry, every state must have a transition for every symbol, right? Which state is missing that it doesn't have, like A, it has 0 and 1. So means state A satisfied and it has transition for all symbols, for every symbols. How
So
about
state D,
state D is missing with transition
1.
1. Similarly, C and E also missing, right? Because it is it's state 1, so it's also missing 0 or 1 is also missing 0 and 1, right? Is it clear? So
Yes, sir.
so what happens? What actually happens if I get 0, 1? If I suppose in the state C and I get 0, where I will go? Suppose my string is 0, 1, 0. What will happen? So 0 I come to B and 1 I come to my final state. Next input is what? 0. From C with 0, where I am going?
So it will discard the zeros.
So, no, here in this machine we don't have self loop. Actually, this language is what? It has at least 1, 0 followed by 1. After that, there are no 0, no 1. So this is not below, this string doesn't belongs to this machine. So if what will happen, we assume that if after at C, if we get some other symbols, which is not part of the machine, then that state actually goes to some state that is known dead state. We call a dead state. So now look at this. If I have 0, 1, 0, this string doesn't belongs to that machine, right? Where we are going? 0, I am B, 1, I am at C, and once I am getting 0, I am going to dead. That means this string doesn't belongs to that machine. Now look at this machine. What happens? For each state, it has a transition for every symbol, isn't it? Is it correct? And what is the difference between C to dead and E to dead? What is the difference you are seeing? There is two transition. One is with 1 and another one with 0. But here I am written only one transition. I label with what? 0, multiple symbols. It's possible. So because 0 or 1, either if you get 0 or 1, you will go to the dead state. So instead of this two transition, I can also write like this. That means either 0 or 1 in the state C, I will go to the dead state. Okay, now this machine is actually perfectly DFA. It follows the principle of this machine, this state machine is followed the perfect definition of DFA. It means deterministic. Means each state I have transition for and for each symbol I am going to the some other states. So what does it mean? Does these labels are not here? This is not a DFA? Huh? What do you say? It is not a DFA? Yeah, it is also a DFA. We assume if any transition are missing, like here one is missing, that means this goes to the dead state. We assume to keep my machine simple. Look at this. If you look at this machine and if you look at this machine, this one looks much complex. Okay, so make the machine look simple. We assume in DFA that if there is any missing label transition, means that transition actually going to the which state? Dead state. Is it clear? So this is actually a DFA. It is also a DFA. Perfectly correct DFA. For simplicity, we don't put all the ages. Okay? Clear? All right. So next class we'll start non-determinism. So this is a deterministic, and next class we have non-determinism, and it is a powerful tools. Okay, so you try to attend to the next class. This will be a non-determinism of finite state machine. We'll start next class. Okay, I have one homework for this. Try at your home. So LW is a language, is a binary number divisible by 3. You already know how to design a machine that is divisible by 2. That means if it ends with 0, you can say it's divisible by 0. Now you have to think about what could be the strings looks like. Example is this is divisible by 3, 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 and so on. So I list some more strings and try to design that finite state machine. And I want to see in the next class you bring that solution of this. Okay? Any questions so far? Saib sir, you are late. Okay, so thank you for your time. So I want to end. Online class is enough. 40 minutes is enough. I consume 45 minutes.